The next question of CODECHEF starters 118 is Xorry1. So basically in this question we are given a integer x. We need to find out any two integers a and b which satisfies the following conditions. A XOR bitwise XOR of b is equal to x. This is the first condition. And A and B should be in the following range. A should be less. A should be in between 0 and x and should be less than b, and b should be in the range 0 to x and should be greater than a. It should satisfy these two conditions, and additionally, and one more condition that it need to satisfy is whatever numbers we print a and b, the difference between b minus a should be among all the pairs of A and B which satisfies first two conditions. We should print A and B which has the difference B minus A as small as possible. So difference of B minus A should be as small as possible. This is the third condition. So as a gist we are given an integer x. We need to find out any two integers a and b which satisfies all these three conditions. A bitwise or b should be equal to x. A and b should be in the range 0 to x and a should be less than or equal to b. And b minus a should be as small as possible among all possible a's and b's which satisfies the first two conditions. So there can even be multiple A and B values which satisfy all the three conditions. In that scenario, we can print any of them. So now if we look at the constraints of this problem, the constraints are test cases can be in the range 1 to 10 power 5 and x can be in the range 1 to 10 power 9. So let's see how we can solve this problem. So here if we look at the constraints, x lies in the range 1 to 10 power 9. So that means number of set bits in the binary of x in the worst case won't exceed 30. Right? So this is what we can conclude. So now we know there can only exist 30 bits for x. Now let's consider a x with some binary. So assuming a x, assuming we have a x with the following binary. Okay. So this is our x with the following binary. So this represents 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 6, 2 power 7, 2 power 8, 2 power 9. Okay. So now, firstly, we want to build two numbers a and b, right? And a should be smaller than or equal to b. So the observation that we can make is first observation. So let's say if I pick 2 power x, then we can notice that 2 power x is greater than 2 power x minus 1 plus 2 power x minus 2 plus so on plus 2 power 0. Right? So if we consider a bit x, or let me name it with a different variable. If we consider a bit I, then 2 power, then though we add up the contribution of all the bits lesser than I, still the value won't be equal to 2 power ith bit. Right? So from this observation, it is simple enough to from this observation, we can notice how do we build A and B. So now it is simple enough to build A and B from this. That is, we know the first set bit because one thing that we know is for A's or B to be equal to X, whatever set bit is present in X, that should be present in either A or B for sure. Then only A's or B will be equal to X, right? So, so now each set bit in X should either be in A or in B. Now from right to left, if we come, then it is always from the below observation, we can observe that it's always optimal for us to put MSB in B, most significant bit in B. That is in this case most significant bit is 9. So B will be 2 power 9. And in A, we can put all other bits. Right? So we can put this, and this in A. So that means value of A will be 2 power 7 plus 2 power 4 plus 2 power 2 plus 2 power 1. And we can ensure and this will ensure that B will always be greater than A, right? Because from the below observation, though we set all these bits to 1, still the value is lesser than B. Still A's value will be lesser than B. So in this case, we are only setting the set bits that are smaller than set bits which are set in X and are smaller than 9. So B will always be greater than A. So this ensures the second condition is satisfying, and this will even ensure the first condition is satisfying. First condition is satisfying because we are putting the most significant bit in B and rest all set bits of X in A. So when we XOR them, the final result will be X. Now, if we look at the third condition, the claim is whatever way we are putting, that is always optimal, and it will always give us the smallest B minus A value. Right? The difference value B minus A will be smallest if we do this. That is because we are always putting the MSB. For sure, we know MSB can only be kept in one, either A or B. And as B should be greater, we'll for sure put that bit in B only. And leftover bits, though we know that though we set all the bits lesser than MSB, still the value won't be equal to B. That means B's B's value is fixed to 2 power of the MSB, which is 2 power of 9 in this case. And for A, it would be beneficial to set as many bits as possible in A. So we'll set all possible lower bits which are set in X to A. So in that case, what happens is if B value is here, then we are trying to bring A value closer to B. So if we know that A value can never reach B, but if we could bring A value as close as to B, then we can ensure that B minus A, the difference will be as small as possible, right? So greedily, we are just placing all the bits in A, which will ensure the A value is dragged as close as to B. So from this, we could even prove that arranging it in this way would make B minus A as small as possible, right? So this kind of arrangement satisfies all the three conditions. And there could be many such values. Like here in B, we kept 2 power 9. So I could have added 2 power 0 and added 2 power 0 to A also. Because though we set this bit in both A and B, it doesn't affect us. They'll still get cancelled out when we subtract, when we do B minus A. So though we set such kind of 0 bits, which ensures second condition satisfies, it's still fine. But one way to find out A and B is just put the maximum bit, that is most significant bit in A, contribution of most significant bit in A, and all other bits which are set in A. Right? Most significant bit in B and all other bits which are present in A. And leftover bits which are zero, we can leave them as zero. We could have set them like we could, if there is a bit zero, then we could have made that bit one set in both A and B, or we could have make it zero in both A and B. Right? So though we set or don't set, it doesn't affect our answer because B minus A will still be smaller. So as we could print any A and B, in our construction, let's consider if some bit is not present in X, let's not at all consider that in A and B. In that way, if we construct, then it is just putting MSB in B and leftover bits contribution in A. So this way we can construct this way we can find out A and B. So regarding implementation, we can just iterate a loop from backwards. And as soon as we find the MSB, put that in B. And leftover bits which are set in X, put that in A. So it is just running a loop of size 30 as there can be at max 30 bits for numbers in the range 1 to 10 power 9, right? As X can be in the range 1 to 10 power 9, at max there can be 30 bits only for any number. If we consider the maximum number 10 power 9, 10 power 9 can have at max 30 bits. So considering till 30 bits is sufficient. So if you look at the time complexity, we can say it is big O of log 2 of x, log base 2 of x. Or if we fix 30 for every test case, we can say it's big O of 30. Or if we perfectly run it till log 2 of x, then it's big O of log 2 of x. And space complexity is big O of 1. So this is per test case. So this way we can solve the problem.